Hi, Kutso. Tell me if you can hear me. Just get your mic going. Good morning. Morning, Kutso.
Morning.
Okay, it's physical science, isn't it?
Yeah.
Okay. What have you started this term with? Where are you at the moment?
School isn't open yet, as far as I know.
Oh, so why are we having class today?
Oh no, I thought it was just some extra work before I go back to school or something like that.
Oh, are you starting next week?
I think so, yeah.
Okay, then we can start with classes next week, with new work, in other words. And today we can do anything you want to. Maybe you've got your results back from your exam. We can discuss
I think I'm gonna get them back next week.
next week. Okay. So what have you done this? We haven't done anything new.
No.
No, I was under the impression that you are back.
Oh, no, it's not that.
Okay. This will help Bernice as well because she's not going to join the class today because she told me she's not back to school yet.
Oh, okay.
Okay. So do you want class or do you want to exit and enjoy your holiday?
No, I can go through class. I actually wanna go through what's this? Mechanics again.
Okay, good. Which part?
Forces.
Like in vectors or Newton's stuff?
They're Newtons.
Newton. Okay.
Yeah.
I don't think we've done that. We've looked at some examples when we did revision, but we didn't do a whole section on that. Oh, we did. There we
Yeah.
go. Well, this was work energy theorem. Let's just delete that. June exam planning we can delete. Good. Okay, so now we're going to add a new section, and we're going to call it Newton. Good.
All right.
Newton 1 to 3. Good. Okay, Newton 1 is just basically Newton 1 you can see as just a bit of theory. Newton 1 has got to do with inertia. And there's no sums there, there's no calculations, there's just a bit of theory. So basically, we start off with Newton 2 examples. You won't, if you haven't studied it recently, you won't know the difference between Newton 1 and 2. Newton 1 is just the theory of inertia, while Newton 2 has got to do with the net force. So all your calculations got to do with net force. So in other words, if I've got a box there or some other object of 5 kilograms, and I have a coefficient of kinetic friction of 0.2, for instance, these all look familiar to you, doesn't it?
Yes.
There's a ball or an object on a rope. The T is for tension in the rope, and that ball is, for instance, 3 kg. Right. That's like a classic example. There's a frictionless pulley system with a rope attached to the 5 kg block, and this system is going to move towards the right and down. So they might ask you, you need to give me a free body diagram of the 5 kg block. That's quite easy. Can you actually help me there?
Mm,
Can you remember that?
I don't have my phone on the sheet, but
You can draw that little picture and then draw a free body diagram, and then you tell me how to draw it.
okay.
If you can remember.
All right. I'm done.
Okay, good.
I don't know how to explain it, but then the force goes up.
The normal force goes up.
Yeah. And then
towards the right,
yeah,
tension.
tension.
Also have friction
And then
towards the left. Now you can call it small f or small f subscript k for kinetic friction. Doesn't matter. And then you have Fg. Okay, you with me? That's fine. That's like easy. So we're doing a very easy example just to start off. And then question 2 might be, what is the tension in the rope? How do I do that? Okay, I have left out a possible question, and a possible question was, what is the kinetic friction? So let's just calculate that before we can actually do the sum. How would you calculate the kinetic friction? The friction kinetic is mu k times n. Remember that formula?
yeah.
Good. Okay, explain. N plus negative Fg equals 0. Just give me a second. I'll be back in a minute. Okay, you have to write that little formula there because you have to get to the fact that the normal force equals the Fg component. You with me? Good job.
Can you repeat that, please?
You have to write this little equation here just to get to the point where your normal force is equal to your G component or your Fg component. So now I can actually substitute that. It's mu k times Fg, and that is 0,2, and Fg is mg. Is that correct? So I have 0,2 times the mass of the object times the gravitational acceleration. And that is 9,8 newtons friction. You're quiet this morning. Have you had some coffee, Kutsa?
No, I haven't, but then I'm still good.
Okay. Right. Now, this is important. What is the method? What is your school's method or your syllabus method to determine something like acceleration or tension in the rope? That is determined by setting up two Newton 2 equations for both objects. Can you remember that? So you have to set up F net equals MA for the 5 kg block. And you have to set up F net equals MA for the 3 kg block. This is not the way we used to do it years ago. I'll show you now a very easy way how to do it, but you're not allowed to use that easy method anymore. You have to use this simultaneous equation method. Right, you with me? So let's choose the direction of to the right or down as positive. Is that correct?
Yes.
Okay, therefore, in my 5 kg diagram, the kinetic friction will be a negative value, while the tension in the rope will be positive, and that will give me 5 times A. While in my 3 kg block, where if I just draw a quick free body diagram, it would look like this. The tension in the rope will be a negative direction, while the Fg component will be a positive direction. You understand that?
Negative. Oh, so you can also make the
tension in the rope must be made negative. Why? The tension, if you look at the 3 kg block, the tension in the rope is an upward tension or an upward force. And so anything that goes up or to the left will be negative, while something that goes down or to the right is positive. If you don't do that, you'll get the sum wrong. So I have negative tension in the rope plus Fg, and that will give me 3A. There's my two equations. Newton 2 equations. Okay, now I can put in the frictional force. It's negative 9,8 plus T equals 5A. And I'm going to make T the subject of the equation. So I have 5A plus 9,8. That is my first equation. In the second sum, I have negative tension in a rope plus mg equals 3a. So I'm going to make tension in a rope the object of the equation again. I'll throw it over to the right-hand side. And then mg is 3 times 9,8 minus 3a. And there's my second equation. So those are my two equations. And I made tension in a rope the subject of both equations. So now I can just make them equal. So 5a plus 9,8 equals 3 times 9,8 minus 3a. And I take all the a's to the left, then I have 8a. And to the right, I have 3 times 9,8 minus 1 times 9,8 is 2 times 9,8, and that is 19,6. And then I get the acceleration. 19.6 divided by 8. So A is 2,45 meters per second squared. Okay, I don't need to get direction there because it's not a question. It's just part of the sum. And then I can use any one of the equations. I'll use the easy one. The tension in a rope is 5 times my A value plus 9,8. That's 22,05 newtons. 22,05 newtons. And no direction, because it depends on which block you're looking at. The tension can either be to the right or upwards. Depends on which your reference is, which block you use as reference. Okay, you need to dot that down or photograph it, whatever. I'm also recording this lesson.
Everything has been written down already.
Good. Just want to show you something interesting. You're not allowed to use this method anymore, but I am going to show you something quite interesting. Just going to copy this and paste this out. So this is what we've just had. Now, there's an easy way of actually working out the acceleration. I'm just going to stick both blocks together. Make it an 8 kg block. Then I'm going to say, what's all the forces to the left and what forces do we have to the right? To the left, we only have a frictional force of 9,8 Newton. To the right, I have only the gravitational force of the 3 kg block, which is 3 times 9,8, and that is 29,4. So the net force on this block system, not on the block, but on the block system, the net force is 29,4 minus 9,8. Are you with me?
Yes.
And that is 19,6. So F net equals MA. The net force is 19,6. The total mass of the system is 8 kg, and I want to determine the acceleration. I'm going to divide that with 8, and then I get 2,45. This is
May I
how
ask?
This is how we used to do it always. It's so quick and easy. Yes.
May I ask, why is this method not used anymore?
It's been used for 20 years, and then they said it's not correct anymore. The guys setting up the syllabus have their own ideas of what we should do and not should do. Okay, there's one valid point, and that is that the blocks aren't moving in the same direction. So strictly speaking, it's scientifically wrong to put them in a linear system. So it's scientifically wrong to put something in a linear system if they are not moving linearly. But that's the only reason they can give us why it's wrong. It's not wrong. It's just they don't want it that way. Just as simple as that. Anyway, you're not allowed to use this. You must use this new system. which is kind of long. Right, let's do another Newton mechanic example on a sloped surface. And I have a 20-degree angle here with another object, which is 6 kg. Right? Okay. So this block is sliding down at a constant velocity. Let me just try and spell velocity right. Velocity. So the box is sliding down at a constant velocity. I want you to draw a free body diagram of all the forces on the block. Please draw a free body diagram.
Is there a frictional force?
Pardon?
Is there a frictional force?
There must be. If
Okay.
there were no frictional force, it will just accelerate. If there weren't a frictional force, look at my free body diagram then I'll have a normal force. I'll have a FG parallel force, and I'll have a FG perpendicular force. If there weren't any friction, then the forces that are parallel to the surface will only be one force, and that force can't be in equilibrium then, so it will accelerate. But since there's a frictional force in the opposite direction, it means that these two forces now can be, the sum of these two forces can be 0. And if the sum of these forces is 0, it's going to either stand still or move at a constant velocity, because there's no acceleration then. So there must be a frictional force. If there's no friction, it can't go at a constant velocity, it will accelerate. Right, so what are they going to ask us to do? First is, they might ask us, after the free body diagram, to work out what is the kinetic friction on the block. Right, I want you to try that on your own. And then you're going to tell me after you've done it, what are we going to do? I'll show you 2 methods to do this, and I'll show you which one would I prefer that you do. And if you don't know what to do, you can just tell me, I'm not sure. Then we do it.
Right. I don't have the values for. I just realized that I didn't have the value for the kinetic friction. I'm saying I just realized that I didn't have the value for the kinetic friction.
Yes. Okay, so what method are you going to do? I'm going to do F net equals MA, Newton 2. You have to write that equation if you're using a Newton 2 principle. And then I'm going to look at the two forces that are parallel with the surface. And I'm going to choose a direction as positive. So the FG parallel component is positive, and the frictional component is negative, and that equals 6 times A. Well, I've left out something. F net is 0 because there aren't any friction. There aren't any acceleration. Sorry. So the net force is 0. So I can make those two components equaling 0. So therefore, the frictional force equals the Fg parallel force. So the frictional force is mg, what? Sine alpha. Remember, the parallel force is mg sine alpha, while the perpendicular force is mg cos alpha. Okay, so the frictional force is the mass of the object. I think it's 6, yes, times 9,8 times sin 20. Calculator. That is 20,11. 20,11 Newton upslope. Right, that's one way of doing it, and this is the preferred method. I would use that method, but I want to show you something else as well. Tell me when you're ready.
Yeah, I'm ready.
Okay. Now, very important. If a block is stationary, so if we have a block on a slope that is stationary, so the acceleration is either be stationary, or if it's moving at a constant velocity. And there are no external forces, so no one's pushing or pulling the block. So it's only the weight components and friction. Then you can also use this equation. Then you can also say that tan alpha equals me. Right, so tan 20 degrees equals the coefficient of friction. Let's do that. Tan 20. Tan 20 is, so me equals 0,36397. So I've got that coefficient of kinetic friction. And then I can use this formula. The kinetic friction is the coefficient times n. This is the other formula. So the kinetic friction is 0,36397. And the normal force equals the Fg perpendicular force. So I can just write the Fg perpendicular. So I have 0,36397 times perpendicular is m times g times cos alpha. So, this is a lot of decimals to write the whole time. The mass is 6, 9,8 cos 20. Let's type that in the calculator. I luckily have that long value still in my calculator. So I'm just going to times with 6, times with 9.8, and times with cos 20. And then I get 20,11. 20,11 Newton up slope. So there's two ways of doing it. This is method 2. I won't recommend that. It's slightly longer, and it's something you're going to forget. You don't have that equation on your formula sheet because it's not always true. If there's any acceleration there, it won't be true. Okay, so I'm going to delete that. Or do you want to write it down, actually?
I already wrote it down.
That's very quick. Okay, so what is the next question? The next question is probably... No, yes, there aren't going to be any other question. This is probably what they want. There's not really anything else to figure out. The acceleration is 0. There's no ropes. There's no tension. This is just the friction they want. Right, so let's expand on this. So again, I have a sloped surface of 30 degrees. Okay. There's a box there. it weighs 20 kg. And then I have a pulley system there with a flat surface. And this block is pulling another block, smaller one. There's no friction here, no friction on this sloped area. And on this 8 kg block, we have, okay, there's tension and rope. On this 8 kg block, we have what? 15 newtons of friction. Do you want to make a difficult example? Yes.
I want to go through this one first.
You want to go to this one first? Okay, good.
Yeah.
I want to know. Okay, first of all, free body diagram of the 20 kg block. Right, that's not difficult. So I have a normal force that's like perpendicular onto the surface. Then we have to the left, we have tension and rope. And to the right, we have a FG parallel component. And downwards, we have a FG perpendicular component. Then I'm just going to draw a free body diagram of the 8 kg just here somewhere. And I don't need all the components. I just want to have a look at the components that's parallel to the surface. So this is the 8 kg block, the red one, and the blue one is the 20 kg block. And I want you to calculate the acceleration. What is the acceleration of that system? Try and figure that out. You have to set up two equations and make it equal to one another. Okay, do you need some help? Good, sir?
No,
Good.
not yet.
All right, good. So I'm just going to make sure you're doing the right thing. You're setting up a F res or F net equals MA of the 20 kg.
Yes.
Setting up one of the 8 kg.
Yes.
Good. And then you're going to make the tension rope subject of equation, and you're going to work out the acceleration. Good. Where are you now?
I'm putting the two equations together now.
Good. Sounds good.
That is an absurd number.
Got it.
Yeah, but
Okay.
it doesn't look right. It looks
Okay.
so absurd.
Okay, let's look at the blue drawing. We're going to choose this direction as positive. Is that correct? Downwards or towards the left?
Yes.
So my FG parallel component is positive, and I have a negative tension in the rope. There's no friction, and that equals 20 times A. So FG parallel is mg sine 30. Minus tension in the rope is 20A. Just work that.
Okay. Okay. I forgot that. The
20
negative.
times 9,8 times sin 30 minus 20A equals tension in the rope. If you type that in your calculator, you should get 98. Minus 20A is tension in the rope. That's my first formula. Second
Yes.
formula. Second formula is the red drawing. And the tension in the rope is positive, while my friction component is negative, and that equals 8A. So tension minus 15 equals 8a. The tension in a rope is 8a plus 15. And that's my second equation. Now I'm just going to make those two equal. 98 minus 20a is the same as 8a plus 15. And then I have everything to the right. Oh, it is going to be funny. 28a is 98 minus 15. That is 83. No. No, it is 83.
98 minus 15, 83.
Yeah, I don't know why I couldn't do that in my head. And that's 2,96 meters per second square, left down, or towards the left, or down slope, or whatever. That's the acceleration of the system. Check that out, dot it down.
It's already there.
Good. Okay, now we're going to freak out this sum. See if we can do something cool. I'm going to have the same everything, except I'm going to take this angle out and just make it alpha. And I'm going to ask you, what should the angle alpha be so that the 20 kg block slides down at a constant velocity? In other words, we should now change that angle. That angle must be less than 20 now, because the higher you make that angle, if you're going to increase the angle, the block's going to slide down faster. You agree? If you make the angle smaller, the block's going to have less gravitation. The parallel force of gravitation is going to be less. So that angle is going to be less than 20 degrees. So I want to know, what should that angle be in order to have a constant velocity? The sum is going to be the same. I'm going to set up a F res or net equals MA of the 20 kg block. And I'm going to set up a F res equals MA of the 8 kg block. Now, the difference is I don't know the angle. But I do know that there's not going to be any acceleration. So in both cases, the resultant force is 0. So let's use our free body diagrams. So it's FG parallel plus a negative tension in a rope is 0. So the parallel force equals the tension in the rope. This is my first equation. I can expand that parallel force and say that is mg sine alpha, and that's the tension in the rope. And that is 20 kg times 9,8, and then sine alpha. I don't have that alpha. I don't have it. And that's the tension in the rope. That's my first equation. And that comes from the 20 kg block. Then I have a second equation that comes off that red drawing of the 8 kg block. And in that drawing, the tension in the rope is positive, while I have a negative frictional force, and that equals 0. So the tension in the rope equals the frictional force. So the tension in a rope equals 15, because the frictional force is 15. And that's my second equation. So that does make it really easy now, actually, because I can just substitute 15 into this bottom equation. So therefore, 20 times 9,8 sin alpha is 15. And now I can divide 15 with 20 times 9.8. So sine alpha is 0,0765 whatever. That's what I get. And then you shift sin answer. And then I got 4,39 degrees. So the angle must be 4,39 degrees. Bang. So what I was trying to show you is that it doesn't matter what they give you. the method how you solve these things are all the same. You set up the equations, you solve it simultaneously.
All right.
Okay, so that's the type of stuff you're going to get from Newton. And there's also Newton's universal gravitational force. Do you want to have a look at that?
Yes.
Okay, so now I have an object here. It's like a planet or something. And let's say it's got a radius of what? 50,000 kilometers. So that's a lot, eh? That's too much. Let's say it's got 500 kilometer radius. And it's got a mass of 2,3 times 10 to the power of 15 kilograms. Right. And then we have another object. So this is A. We have another object. Its radius is not applicable. So the radius is not applicable. It's too small. The mass is what? 6,000 kilograms. Right, I want to know, what is the force that A exerts on B? Remember that formula. F equals G M over R squared. And G is a constant. G is 6,67 times 10 to the power of minus 11. And that is in Newton times meter square times kilogram to the power of minus 2. So that gives away all your units. In other words, I'm not allowed to work in kilometers. I must work in meter. So you want to convert this 500 kilometers into meters, which is very easy actually. It's just 500,000 meters. Okay, now, what is the force that A exerts on B if the distance between their surfaces, the surface of the two objects, is what? Let's say 250 kilometers. So from this one surface to B is 250 kilometers. Now, the first thing you must realize is that this universal gravitational force, or Newton's universal gravitational equation, you have to calculate the distance from the midpoints of the two objects. In other words, my distance, which is R, we're going to add the radius to that distance. Do you understand that? It's going to be 750 kilometers. Could you remember this, good sir?
Not much.
Okay, so I'll do this example then. So the force is G, the mass of the one planet times the mass of the other object over the distance squared. So I'm going to use 6,67 times 10 to the power of minus 11. And the mass of the one object, let's call it A, is 2,3 times 10 to the power of 15 kilograms. The other mass is 6,000 kilograms. And I'm going to divide that with 750,000 meters squared. I get the 750 by adding the radius of the planet to the distance from the surface to the other planet or other object or rock or whatever it is. Because I have to use this whole distance as a R value. Can't just use from the surface to the other surface. It must be from the midpoint of the one to the midpoint of the other. And that you can just type into your calculator. That's very low force. 1,636 times 10 to the power of minus 3 Newton. Attractive. It's an attractive force. All objects with mass attract other objects that does have mass. Please jot that down.
Okay.
We're going to do one example and then we're going to knock it off for the day. This is the one thing in Newton's universal gravitational law that you must be able to do. Just work out the force or the distance between two objects. The other one is what happens if something changes. Now, say for instance, this is Earth. There we go. There's like, there are you. You are like falling down or jumping, free fall. You're being attracted by the Earth, and that's why you're going to fall. We can't put a parachute in now because that's going to just destroy the acceleration that you are. So we're going to assume that you don't have to fall towards Earth. You can be standing on Earth as well. It doesn't matter really. Okay, there we are. There we go. Okay. Now, then you move to another planet. Let's call it P. Okay, there you are. Right, planet P has half the radius of the Earth. It's got half the radius of the Earth. It also has half of the mass of the Earth. So that's a smaller planet. It's half its radius, which is much smaller, and it's also got half its mass. I want to know, what is the gravitational acceleration on P? Will it be more or less than that of the Earth? Remember, the lower the mass, the lower the force, the lower the radius, the higher the force. So there's a way of doing it. I'm going to show you exactly how to do it. You're going to use Newton's universal gravitational formula. It's G times mm over r squared. And that is true for the Earth. So in other words, look at this, very important. So if I convert the force that the Earth exerts on you is basically the same as mg, the mass times the gravitational acceleration. That is big G mm over r squared. So I can actually cancel your mass. Very important. It doesn't matter how much mass you have. If I compare a brick to like a feather, the Earth, the acceleration of those particles or those two objects are exactly the same towards the center of the Earth. So your mass is irrelevant. So the gravitational acceleration G is 9,8 on Earth, and that equals G, that universal constant, times the mass of the planet, in this case the Earth, times divided by the radius squared. So that's, if you type those values in, you get 9,8. Right, now I'm going to do exactly the same on that other planet. That planet is also attracting you with a certain force. It's also G value times the mass of that planet times your mass divided by the radius of that planet. But the force that that planet uses is also called mg, your mass times the acceleration, gravitational acceleration of that planet. So the mass, your mass is also irrelevant here. So I can cancel it. Okay, but those values didn't stay the same. So let's just revert. Show you how we can fill in those values. So F is mg, then we have big G, then the mass of that planet is half the mass of the Earth. So if I want to compare it to this formula on the left-hand side, I must just do a half m because it's half the mass of the Earth times your mass, which is going to be eliminated. And the radius of that planet is half the radius of the Earth. So in that case, G equals big G, half M, over a quarter R squared. Now a half divided by a quarter is 2. So G equals 2 GM over R squared. Because that half divided by a quarter is 2. So I can write 2 in front. And that value there is 9.8. So the gravitational acceleration on that planet is 2 times 9.8. It's higher than the Earth, which is 19.6 meters per second square. Downwards. Look at this. Write it down. This is just the overview of some of the Newton stuff that you must be able to do. And then you're going to let me know by next week sometime, what work are you starting with? So I can get some stuff together.
Okay.
You happy?
Yeah.
How do you think your test went? Well.
Yeah, I do really think it went well.
Okay. That's very good news.
Yeah.
Okay, Kutsu. We are knocking off early today because we don't have much to do. Or let's say we don't have anything specific to do. But next week we'll be working flat box again.
All right.
What you need to do is just find some examples. If you haven't started with new work, just find some examples in old papers on Newton stuff. And then we can always do it next week if you're struggling with some of it. But it's important to have a memo with you while you're studying. You understand?
Okay.
And actually look at the answers. Excellent. I'll chat to you again.
All right. Thank you.
Bye-bye.